Thank you very much. First of all, I would like to thank the organizers to letting me speak on my first SciPy conference. It's very exciting, but also very terrifying. I would like to introduce myself. I am a direct fellow at the University of Washington at the Astronomy department, but I'm spending most of my days working on Astropy, AstroML, and other sorts of software projects. So the field in astronomy has changed dramatically in the last 10 years, and Python became the de facto standard, the language of choice in all groups on the career ladder, and there are a few surveys to show that already. So this one is done by Eva and Eric a couple of years ago. It already shows that even the faculty are choosing Python. This is another version of the same thing, is looking into the astronomy literature and searching for language references in astronomical papers. And Python is just exponentially going to the sky. The reason behind this is really difficult to see. We think that part of it is the success of Astropy, but also the part of the success of Astropy is also because of the language of choice is Python. So it's difficult to disentangle. So what is really Astropy? So Astropy is a shift in attitude towards open source software in astronomy. Astronomy was always a field that was very open with its data and with its software, and open source software existed in astronomy for a long time, but it usually meant that the software was dumped on the internet, or you could ask for it and got a copy of it, but it didn't mean open development. And Astropy started doing this movement of the software shouldn't only be open source, but openly developed, which means that the development process, the commenting, the decisions are made out in the open, and the community of astronomers and software engineers can participate in that. It's not behind the wall of an institute. You don't have to be an employee of a certain institute. You don't have to have powerful supervisors as a student to be able to participate in an activity. So this whole community effort is to develop something common good that is used in the whole field of astronomy. That is Astropy. So the project had the aim to develop a common core package and also a whole ecosystem of interoperable packages. So when I talk about the core package, I mean Astropy, that you pip install Astropy or import Astropy. And then this package has more than 300 individual people contributing to it, which, as in all open source, is a wide diversity of single-time contributors to people who are doing contributions every day. In average, we have 20-25 active people on the project every month. And we also, in a healthy, close to healthy ratio of issues. So the number of issues being opened is not going to the sky. They also got closed. At the end of the talk, I would like to reach out to other folks who have better, already at this conference, I saw better visualization to show the same thing. So the roadmap for Astropy is, for the core package is set. We do have releases every 6 months. We don't necessarily decide years ahead that which release will ship what feature, but we do the release nevertheless. Even if we planned to ship something but it didn't get finished, we are not waiting for it, we are doing the release. We usually see ahead for half a year or a year and have vision beyond that, but that's really a vision, not a roadmap we are working towards to. And for big changes, we decide via the process we call APE, the Astropy Proposal for Enhancement. It's the very similar idea as the PAP, and then what other projects also started to do very recently, like NAP for NumPy. We are doing it for almost since the beginning of the project, so back in 5-10 years. And then in many times our feature releases have one big idea that is new in it. For the last two, I listed the last two. So a year ago, we tried to improve performance. And then in the last one, we added a new sub-package, the time series sub-package. We also do long-term support releases because many of our power users are research institute and astronomical observatories, and they require API stability and then the guarantee of that. They would like to use new features, but it's more important for them to not need the ability of not to be pushed to update all their software. So we do this long-term support for 2 years and guarantee that there won't be any API changes. And so what lands in the Astropy core package? It collects commonly used functionality that is useful for most of astronomy. For example, coordinate transformation, handling of physical constants and units, data modeling and fitting that are aware of these units, and the I/O of the most frequently used astronomical data, files, containers. And some numbers about the Astropy core package. The numbers are almost a year old. We are waiting for the new GitHub feature to reach our repository. We still don't have those numbers. So this data was mining GitHub, and that means that these are lowest estimates. So I could only go into the repositories and look into them if they were public and they were hosted on GitHub. So we have one dependency, that's a mandatory one. We depend on NumPy. We also optionally depend on other packages in the scientific Python ecosystem, but we only require NumPy, and that helps enormously. And then a few words about the team. We heard this past few days that it's a really difficult question of how you phrase who is your team. So on the picture, I took it the code contributors to GitHub, but then we also have a very detailed team page that also shows non-code contributions and non-code roles in the team. The top of the governance is 4 people doing the coordination committee. It's mostly project management and running the project. And then code-wise, there are the deputy and lead maintainers of the different modules. It's about 20 people. These 20 people have the right access to the repository. And then we have the contributors, which is above 300 right now. And then we like to use this word in Astropy, duocracy. That means the tasks, the features get done if someone is doing them. And then the decisions are about how the API should look like or what can land in that needs a community consensus and agreement, but it will only happen if someone is stepping up that, okay, I do it. We decided we need it, and I'm willing to do it. This can be either an individual who has some interest in doing that job, and it also can be an institution who would need that for their operation. And we have examples for both. Most of the work is done in remote collaboration. There isn't a central institute that oversees Astropy. It's an international collaboration, not even bound to one country. But we also try to have face-to-face meetings every year. And as I mentioned already, Astropy is not just the core package, but the whole ecosystem. And we call these other packages coordinated or affiliated packages. Coordinated packages in Astropy land means that it's the same team who maintains the core package, maintains those coordinated packages, but also we have the affiliated packages, which are more loosely connected to the project. All of these packages agree to adhere to Astropy's coding, documenting, and testing standards, and that they are using Astropy and the other part of this ecosystem whenever possible. They are not reinventing the wheel. They are not re-implementing a coordinate transformation, a framework when it's already available. If they find some issues with it, they are encouraged to contribute to that package that already implemented it. And then in exchange, the core team provides some infrastructural help for the packages that would like to have this. And then I will detail these packages later on in the talk. And some example for the affiliated packages, we have roughly 3 categories of them. Packages that has functionality under heavy development, they might contain core functionality and they might end up in the core package later, but currently the speed of the development is not suitable for the half-year release cycle of the core package. Their API is not stable, so they are still in a separate package. An example is astronomical image reprojection, when you have images in different coordinate systems or axes, and then you reproject everything into one. Or a re-implementation of the hill picks with BSD license, so we will be able to include that in Astropy. And there are also packages that has more specialized functionality. These packages won't end up in the core Astropy because it's only a subset of astronomers who are using it. Examples include Gamma Pi, which is a package that's only used and useful for gamma ray astronomers, which is a small subset of all the astronomers. Or AstroML, which is a machine learning library for astronomy. Although from AstroML, certain parts actually ended up in Astropy. And then also packages with incompatible licenses can be affiliated packages, but obviously they will never end up in the core package. And just showcase 2 examples what is in Astropy. It has certain functionalities that can be useful not only in astronomy but in other sciences. The whole unit module with physical units, hardly there is any astronomy in there, except that we have some astronomical units, which probably the parsec is not that useful for a biologist, but certainly you can measure cells in parsec. Why not? And then, so 2 examples here. One is that we have multiple implementations of the Lomskargo periodogram in Astropy. This is good for detecting periodicity in unevenly sampled time series. So we have 6 implementations, while in SciPy there is 1. in Astropy, we follow the route of extending core libraries like SciPy and NumPy, where our data sets is either tiny bit specialized or just need some extension. And then the other example here is source detection on 2D images. Most of astronomy is taking photos of the sky, and we need to find our sources, either extended or point sources. So we have quite a lot of implementation of different source of detection, source finding algorithms, and this can be used in other fields of science. We know about cases when these are used in biomedical imaging or other fields where the task is to find sources. And then who uses Astropy? It's really difficult to know. We don't do telemetry. We do publish papers, and then we know that when people cite our papers, they use it. There are people who use Astropy, might not cite it, so we don't know about them. And then we also know about when we get direct feedback. And knowing about usage outside of astronomy is basically we only know about them when we got direct feedback. And there are a few cases when it also hits national news, using Astropy to detect wildlife in Africa. And then this is just to showcase the inspiration for this whole talk, is when Jake van der Plas said on Twitter that Astropy has the most amazing infrastructure out there. And given that infrastructure is really invisible, I started thinking about, okay, how can we show what he really meant? What is Astropy infrastructure? So I think one of the strongest part here is that we have detailed documentation and for developer guides. It's including coding style guides, documentation guides, and how to maintain a package. We also have a fully worked out pull request example. So if someone not working with Git every day, they can walk through it and can see that which file they need to edit and what it means that you need to add a test. And then the other important part of this infrastructure that we have a very detailed testing for each and every commit. And then we require documentation and testing for all pull requests. In this extensive CI testing, we are testing against different versions of dependencies, even against developer versions, so we are able to pick up if there is an issue with development version of Matplotlib or NumPy. We are checking the documentation build, and then we're making sure that all the changelogs and milestones and everything is consistent throughout the development process, not just before doing a release. And the other very important part of this infrastructure that we provide help to other domain scientists to maintain their own packages. And the most important part of it is the Astropy Package Template, which builds on a cookie cutter. People can choose what part of the infrastructure they would like to use, whether they have C or Python code, they want to support Windows or not, and then at the end they get a skeleton with all the configurations set, the same way as it is all the other Astropy packages. So if they already used to how the structure works in Astropy, they got a very similar familiar setup, or if they don't know it yet, it will be much easier for them to contribute to Astropy and the rest of the ecosystem. And then it will be also easier for us to provide them some help. Checking on the GitHub statistics again, more than 400 packages using this template. The other important part of this is Aster PI Helpers. Many part of this infrastructure is started at the beginning of the Astropy project many years ago, when the more generic Python ecosystem wasn't as mature, and then we needed some functionality that was not yet available. So we are constantly reevaluating whether we still need this infrastructure or not. And it's all done through the ape procedure. So there was an ape about Aster PI Helpers. Do we need this? So this is a package to help build Astropy and other packages. But now setup tools is mature and good enough, so we can remove it and actually discussing how to do this, how to remove a critical part of the infrastructure without causing disruption. We also maintained from the beginning certain plugins for PyTest and swings that were not available, and we, over the years, originally started within Astropy, but we factored them out, and now they are available for the wider community to be used as a standalone packages. Right now, we provide PyTest plugins and swings extensions for API documentation. I'm afraid I forgot to mention the avatars of the people are the top contributors to these certain packages on each page. So these extra functionalities that we needed in PyTest, for example, that in many cases we test with data files that we don't bundle with the package, but we would like to test with them, but then we need a way to only test them when we can, when those files are available, when the internet is available, and then just turn on and off these options. When we test against different NumPy versions, there will be some floating point issues with comparing doc tests, but then PyTest doc test plus make sure that the test won't fail on those rounding errors, and so tiny features like this. So another big part that is used well beyond the Astronomy packages is called CI Helpers. We run into the issue that when something got broken in Travis or in Anaconda, Miniconda, or in PyTest and swings, we needed to change many Travis configuration files for our 50 packages. So we started in a central place to provide an easier way to control continuous integration configuration. And to our biggest surprise, this is the one that has the widest usage from our infrastructure, and then people are also contributing back. The deal here is that you basically use 2 lines in your Travis configuration, and then or appware, and then the rest is set by environment variables. You don't need to worry which order you need to install those dependencies. You just provide a list, and then you can set their versions if you want to do different versions very easily. And then we also have certain bots. I know that many projects have bots, and my big vision is that we reuse our bots and then maintain one set of bots only. Our ones are doing so we have a very generic framework with configurable bots and functionality. The ones we usually use in Astropy are to providing a single click to look at the generated narrative documentation in each pull request for each commit, checking whether milestones and changelog are consistent, and we are also building an automated labeling system. And then we also have random tools like every project, and it would be very useful to share those random tools. What is the next pull request number in the in the repository, and so those tiny things. And so this is the big vision, that it would be so good and great to see more collaboration between the scientific Python ecosystem to work on these infrastructure tools. So in the past, we had a few examples when Astropy maintainers were also maintainers of in other projects, and that's really useful. We might want to do that more often, but then the time is limited. We also had examples when something developed in Astropy, originally for Astropy, ended up somewhere else. One example is the image testing PyTest plugin. But then the last 3 points are still outstanding and would be very useful, I think, to find solutions to those. One is to figure out a way to test each other's development versions and build up a good feedback mechanism. The other is to find ways how to discover relevant downstream issues that affect the upstream package, and then also to reach out and have a central place for maintenance and governance tools. How to plot the health of the project, how many contributors we have, are the issues are offshooting and going out of control. We don't need to do that in Astropy and in NumPy and in Matplotlib separately. Ideally, we only do it in a central non-focused repository. And so that's my pitch for tomorrow, for the sprints to start doing something about it. Otherwise, thank you very much for your attention.
It sounds like you just gave me work, so I'm glad I'm not going to be here tomorrow. I got one back here. Awesome.
This is Tom Beard. I talked to Eric yesterday about the possibilities for, I guess, what would be an upstream process for y'all, and an ability to go ahead and start analyzing some of the optical processes that actually occur before you receive information in Astropy. Is there any plans or effort to maybe address that in the future? Should I clarify? Sorry. For instance, if I'm receiving information from the James Webb Space Telescope, and they've gone ahead and given me some information that allows me to go ahead and do further things with Astropy, would I try to go ahead and try to model or include any calculations based on some of the optics that are actually generating that data?
Well, so Astropy is very generic. So our modeling framework, you can model anything with it, really. So if you have data coming from the James Webb, I don't see why not. You can't do that even now. We don't bundle any data into Astropy. So it can be used with James Webb data. It can be used with VLT data. It's not data bound.
Yeah. And I didn't mean to put you on the spot. I just see that if you can go ahead and look upstream, that all of a sudden maybe you have opportunities then to deal with other imaging systems and other sensor systems that have nothing to do with astronomy. So.
Yes, sure.
It's more a suggestion than a question.
Hi, mine is more a question than a suggestion. What is the mix of expertise of the people that are working on Astropy? Obviously, the astronomers need to be in charge of determining what the priorities are, but presumably everyone that's doing development isn't, a PhD astrophysicist or something. And so how do you find people who aren't astronomers but are capable of making good contributions, and astronomers who know how to interact with those people?
That's a very good question. So contributors to Astropy and maintainers of Astropy have rather diverse background. So I would say half of us have astronomy background and half are engineers. And I would also guess that about half of the team has PhDs and half don't. So it's a mixture, but it's always difficult to find an engineer who has interest in astronomy or in research software, because they can be engineers anywhere. So for hiring, that's difficult. Otherwise, we have very varied issues that software engineer could pick up and work on it. Some of those are more astronomy specific, and then a more closer collaboration is needed. Some of them are very technical, which, yeah.
And with that, we thank our speaker.